Alright, Microtronic fans, the SMD bubble LED display version of my Arduino-based Microtronic emulator is finally ready. So I already showed one little video. In the meantime, I put on the lens filter here. Not the best solution, so I probably try to 3D print some kind of holder to keep it in place. But it's always stunning how much of a difference in terms of contrast and LED readability that piece of red plastic, or I should say red filter, really makes. So, little review of the SMD chips on board. This is of course the display controller and keyboard controller, the TM1683. Then here we have the 80 mega 328p clocked at 16 megahertz. So the crystal you can see there, that's still a conventional crystal, not an SMD crystal. And it also has the 22 picofarad capacitors there on left and right. And then we have an EEPROM here, the 24LC256. So with that I can actually store 42 full memory dumps using bank numbers basically from 00 to 41. And then here we have input and output driver chips. So to protect the 80 megas inputs and outputs, the GPIOs. And of course here we have the 4 digital outputs, the clock signal on the left, and the 4 digital inputs here. We have a buzzer on board and we can turn on and off the buzzer using the second switch here. This is a power switch, and then these two switches are used to turn on and off the EEPROM line. So here's a programming port, AVR ISR port, right? This is a voltage regulator, 7805, and then I printed all the mnemonics here. So unlike the other versions of the Microtronic emulator, some of which have an OLED display, you can even read the mnemonics on the display. This is of course machine code only. And then of course we have the gorgeous LED 7-segment 6-digit bubble display, which I got from Jamaico Electronics. And this one here is the status display. Currently it shows halted, right? So if I start entering instructions, right, program it, then it turns to A for entering address, and of course it has from 00 to FF 256 addresses in RAM, and then we can just enter instructions, and P means mnemonics, right, opcode input, right? So if I do a little counter like this, I say okay, display 1 digit starting at register 0 on the display, and then I'm adding 1 to that register, and then I'm going back to address 1 with a goto, right, and I start that program. And then now that display changes to R for run, and you see it's running. You can also change the emulation speed by pushing run and a number, so that's the fastest speed here. And then I can slow it down by, you can actually see what's going on, right? And here, this is the clock signal, right? 1 Hertz clock for the internal clock. Then we have the power LED on the right. Then we have carry and 0 flag, right? And the other 4 LEDs here are the digital outputs, which I can also demonstrate. So how about we also output, FE0, that means output the content of register 0 to the digital outputs, FE0. So you can actually find that opcode here on the table, right? If we look at, here it is, dot data output, right? FES, and S is the source register, so FE0 it is. And let's go to instruction address 1, and let's run it again. And this time we will also see that now the LEDs are counting in binary, right? And the buzzer is connected to the force LED or the force output, right? And I can turn this off here with the second dip switch if I want to. Let's turn it off. There you go. And then of course a single stepping is also possible using the step button. And since it doesn't go back to the display instruction, it never shows the display again, right? It shows go to 0, 1, add 1 to register 0, output to the digital outputs, right? And do that in a loop, so we can see that the digital outputs are changing, the LEDs, but we don't see the register anymore. But we can use the rec button, register display button, to actually see the content, right? So currently there's an A in the register. I can also edit and change the register value if I wanted to. So by pushing next, I can continue stepping through. And yeah, so that is that. And my favorite game is 17 and 4. I think it's called Blackjack, right? It's one of the ROM programs. There it is. I just loaded it from the program space memory where those are stored. EEPROM is one of the ROM programs, so there are 16 ROM programs. And so computer gives you a card, a random card. Now I have 7 and the computer has 7. I can decline using 0 and I can say give me another card using 1. So of course the goal is to get as close to 21 as possible, 17 plus 4. So I want another one. Okay, so now I have 17. That's pretty good. So I stop. So I use 0. And indeed I lose because actually the computer got 20 and I got 17 only. All right, another round. So I got 4. Of course I need more. I have 7. I need more. 14. Yeah. Well, I think I have to get one more. And again I lose. Now I have 22 and the computer has 17. Well, sometimes I win, but it's rare. The computer is not cheating though, it's just random. So I decline here. Still 15 was outbeat by 18. Yeah. Last run. No. Oh, come on. The computer reached 21. And then of course you win immediately, even though I only had 13. Ah, this time I win. Good. So I got 21 and the computer got 14. All right. Other nice programs in memory are prime numbers, PGME. And you can either enter a number and you want to get the next prime number after that. So let's start with 100. Oh, I hit the wrong button now. So what's the next number after 110? Next prime number after 110 is, that takes a while. So this is the emulation running at max speed. It's 113. Makes sense to me. Yeah, and of course this is running on battery. I don't know for how long, probably 3 hours or something like this, because the LEDs, they draw quite a bit of power. Another nice feature is using the EEPROM and the core dump basically facility. I can now store the program to the EEPROM and load it back, right? Non-volatile memory. EEPROM2 is dump, core dump, and now it's waiting for the bank number, which is from 00 to, I don't know what 41 hex is, but it has 42 slots. So let's dump it to 0, 0, and so now it has been written to EEPROM dumped, and let me clear the memory and I can load it back. So memory is empty now. 000 is no op, and with Hoid PGM1 I can load it back from the EEPROM. Call load, and bank number is 00, and I loaded back the prime number program. Here it is again. Of course, I mean the prime number program and 17 and 4 are also in the program space as ROM programs basically. So this was of course only for a demonstration, but obviously I could use the same core dump facility to store my own programs there. So let's do the other classic counter that I always demonstrate using all 6 display digits. So I'm counting 1 to register 0, and then I'm moving register 0 to 1, to 2, to 3, to 4, to 5, and I'm displaying all 6 registers from 0 to register 5 on the display. So they are all counting in unison. Next 0, 0, run like this, right? And this is the max speed. Can slow it down again, max speed. And maybe one more demo of the single stepping. So if we actually go back to the display instruction using go to 00, where the display instruction is, F60, then of course you also get an updated display when you single step over it, right? Other features are you can set a breakpoint and so on, right? So, but let me now store this program into EEPROM. This time I'm using slot number 101, right? And I can load it back. Right, PGM5 clears the memory, and load it back using PGM1. Core load 01. And there it is again. If I load 00, I should be getting the prime numbers again. There they are. Alright, so that's the demo for now. Thanks for watching.